So I'm going to talk about macho reanalysis results without the results. So as you guys know, in this business, often making slides right to the end, and sometimes the results don't come through before your slides are done. So I'm going to talk more about the analysis process and some of the challenges that have come up and why we think we can do this and so on. So the motivations are, I think, well understood by most people in this room, but the big thing is that machos can exist. There's not really much theory that says they can't. There's some informal constraints that come with a lot of assumptions, and then there's microlensing constraints. But the big thing is that supersymmetry seems to be breaking above the LHC level, or maybe it doesn't exist, but either way, WIMPs seem less likely than before. And then also, from the black hole community, the theorists say that machos can form an extended mass distribution that can fit under all the constraints anyway. So there's reason to do this, and microlensing provides the most direct way to make the measurement. There's also some indirect evidence. So this is a globular cluster that potentially has an intermediate mass black hole. That's interesting because this mass doesn't really have a stellar counterpart. And then there's also high redshift quasars, which if you backtrack their observed mass, they seem to need some sort of seed mass, which is not explained with normal black hole physics. There's also LIGO, which we all know about. And here's this plot that Will and I made, Will Dawson, for the LSST dark matter white paper, which you may or may not have heard about, but there's a draft at this link if you want to look at it. So here's all the constraints on machos across the entire compact object mass range that you might be interested in, all the way down from evaporation from gamma rays, M31 microlensing with Subaru, and then the microlensing from the Milky Way with Eros, Ogle, and Macho. But with LSST, we can actually do a lot better if we include paralensing or parallax detection of microlensing. So without parallax, at the short time scale, you had this curve come down. This curve is actually the sum of the two. So we know that this disappears with this constraint similarly, but if we include the paralensing, we can actually go much higher because the yearly time scale of parallax is very powerful. And so, but there's a bunch of challenges. So first is that there's really not a lot of signal in the parallax for most orientations. So we have this mass range that we might be interested in, and we have this distances for the sources, but most of the time, the parallax is really small. Second, there's a large diversity in what parallax can look like. I mean, these are just a bunch of injected signals that I added to a macho light curve, and there's a high diversity of sources and a lot of degeneracies that you have to sample through with your algorithms. Second, it's that some stars are just variable stars, and this is a big problem for the long time scale variability. It's even possible for the variable star to have something like a yearly time scale, and the bulk of the signal is achromatic. I mean, if you zoom in, there's definitely some achromaticity, but if you're trying to use parallax on detections, this is an important background. And finally, the bulge observing season there's gaps, and therefore there's aliasing, and sometimes that aliasing can look a lot like parallax. But there is some helpful features about parallax. It's still achromatic, and its periodicity is fixed, so we know what we're looking for. And then also for these longer timescale events, we have astrometric microlensing. So we kind of have this triad of things that we can use to rule out what we're looking at. So here's some interesting light curve from Macho. Here's some template that I use to detect it. It's not microlensing. You can tell it's a variable star. And the time scale is very small, so we can rule out microlensing with this. So we have the Macho database. This is what I'm analyzing, and there's 100 million stars or so. How do we cut that down? We can't do an MCMC fit on every single light curve. It's just too expensive. So the big thing is that the heliocentric or standard point source point lens without parallax, most of the signal's there, and so you can see the signal grow over time. This is just in the data points, just for this 1 year of data. But the parallax is much smaller. So we really should be selecting candidates with the heliocentric templates. So I'm doing that, and I built this template catalog based on some expectations of what we're going to find. But the big thing I'm doing that Macho didn't is I'm allowing the templates to go off the survey, so I can detect with just the shoulder. We all know that's challenging and presents a lot of challenges, but I wanted to not throw away anything. So the way I did it, oh, sorry, I should have talked about these likelihoods. So the way I did it is I convolved all of these signal match filters with every single light curve in the Macho database. So there's something like 1 trillion likelihoods calculated here. This took a lot of CPU time. But I'm also calculating the likelihood that the light curve is drawn from Gaussian noise, and then also that the color information is drawn from Gaussian noise. And I'll use these 3 likelihoods to make some cuts. So here's the blue dots are all the A-graded Macho bulge events from Thomas et al., who reanalyzed the Macho data set. And the points are all the likelihoods. So this is the likelihood of the template. This is the likelihood ratio between the template fit and the Gaussian noise fit. And this is the color likelihood. So the bulge fit, or the bulge events that we know about seem to be peculiar. Now there's some contaminants here which are interesting. So these are events that have high likelihood and high likelihood ratio. So that means that the template was a good fit and it didn't look like noise. So, it looked flat. There wasn't any color variability. And so for this to happen, this is actually, my assumption is proper motion. The stars are moving outside of the fixed PSF. So this begs us to go back to the pixels as well. But I've only been working with the light curves. And then there's some contaminants here for the color versus likelihood ratio, which you can't really see. There's some fine points up here. And these are extreme variable stars that they don't look, I mean, there's a decent template. It can fit part of the light curve, and it doesn't have, and the likelihood ratio is high because it looks very non-Gaussian. So I'll need to figure out how to get rid of these a little better. But if I make a cut just on anything that's near the blue points, there's still 10 or 20,000 light curves that I need to fit with my MCMC. And I'm really just throwing Livermore's computing power at it. So when you do an MCMC, you got to worry about things like step sizes and how to propose the next step in your MCMC. And so to look at this, I injected some light curves of different events that you might want to be able to detect, and looked at the local posterior near there. And you can see that there's a lot of degeneracies in the parameters. I'm not going to go through what is what, and they change. So sometimes they kind of go this way, and then that same parameter can flip and go the other way. You can see here and here. That's really challenging. So when I make a step in my MCMC chain, something can jump off and be in a region of flat parameter space and sit there forever. So this is challenging, and I'm not calculating the Fisher matrix for every event and deciding how to step, but just need to keep these in mind when you're doing your sampling. So here's just some injected data, and this shows a lot here. So this is a relatively flat light curve from Macho that I injected the solid green signal. The dotted green signal is the template that caught it with the heliocentric parameters. And then the black solid is the maximum likelihood fit from the MCMC chains. This didn't really take a lot of steps, so it's not expected to be a good fit, but just wanted to show that you can do it. Here's some other ones so you can see what things might look like. And you'll notice these all have pretty high parallax, which isn't necessarily what you expect. Now here's a long time scale event you might want to be able to detect, and you can see that without a good measure of the baseline, you can get really far off. And so this shows that even in a 7-year survey, this is still going to be challenging, even if you find the peak. So here's one event that passed all my cuts. It's Macho bulge 12. I like to think of it this way. If you, so I freed up the parallax period, and I guess I found an independent measurement of the Earth's orbital period if you assume that it is indeed a microlensing event with parallax. But it's doing pretty well. This is not, I mean, these are pretty uninformative priors, and I wanted to talk a little bit more about that. So yesterday, a bunch of stuff came up with Bayesian analysis, and I just wanted to talk through some of these concepts. So the likelihood is kind of what frequentists like to stick with. It's the data, it's the measurement model. And when you say that you have an uninformative prior, you might be saying a lot more than you really think. And so I left everything you've seen before. I left the prior on pi e flat, which is not right, because for most orientations, we can see this drop off really fast. So I just want to show the effect of what that does. So I started with this known Macho event from Bennett, and you can see that by leaving the parallax really high, this gap in the data, some aliasing happens. So there are a couple points you can see barely right there and right there, and you can see them pulling down the median model. But by adding just a little bit of adding a prior to show that, or to expect less high parallax events, it starts to smooth this out. Now, this wasn't a very strong prior, but if I add a stronger prior, you can see it starts to really pull this down. And so there's a lot of scatter here because I didn't really do a lot of steps, but it's important that you include priors that are physically motivated. And when you say uninformative, you often think flat, but flat might be much more informative than you meant for it to be. So yesterday, there was a conversation about concern for assuming something about a distance prior, and there's a lot there. So there's a nice paper, and my slides are a little out of order now because I threw these together at the end. But if you, this series of papers are talked about estimating distances from parallaxes. And I really recommend reading these. These are just a really intuitive and nice explanation for when you assume priors, what you do. So a flat prior on distance is not uninformative like you might think. It actually tells you something what you think about the distance or the volume density of sources when you assume a flat prior, and it's actually very informative when you think you're doing an uninformative prior. And then yesterday we were talking about modeling binary sources versus binary lenses. If we believe that any source can be binary and any lens can be binary, it's actually the proper thing to do is sample between those two options in a hierarchical model and do that full sampling. And then the other thing was the galactic model. Your galactic model has some uncertainty. You should be sampling through those parameters to incorporate that uncertainty. So the assumptions you do in your sampling, when you're trying to do uninformative things, can actually cause problems. And it's more informative than you believe for it to be. So just things to think about. And so that's all I have. So these last few slides kind of came together last night when I couldn't sleep, so that's why they're out of order. But I hope that's informative for everyone. Thanks.
Questions for Nathan? Folks are digesting your thoughts and their food at the same time. Scott.
I have a philosophical question maybe for you and
Sure.
for other Bayesian experts in the room. Is there really such a thing as an uninformative prior?
No.
That's a word that we use to mean log uniform or uniform.
Yeah, I think it's something that came from frequentists, is my impression. People are afraid of using priors because they feel like they're kind of tipping the scale on their analysis. But your prior it's designed to be informative. It's your prior knowledge, and we always have some, so we should put it in when we can. Yes.
So I didn't understand whether you're going through the 100 million light curves or the modular events.
I'm going through all the light curves. I downloaded every light curve in the modular database and convolve those with those heliocentric models. And
the heliocentric models are, have 2-3 parameters. So you're doing a grid search on them. What do you?
No, so I made like tens of thousands of these models across the 3 parameters and just tried every single model on every single light curve, and then calculated all those likelihoods and then made cuts on the likelihood spaces.
But what are the 3 parameters?
T0, TE, and U naught.
Okay, but you still have pi.
Yeah, I didn't include parallax on the detection on that detection step. I called down the light curves after that.
But what does it mean heliocentric if you don't know the parallax? So how do you have a ground-based curve without?
I guess when I say heliocentric, it's as if you're a heliocentric observer, which is like setting pi e to 0.
Okay, well, let's thank Nathan again. Okay, our next speaker, Aparna Bhattacharya, is going to talk about first results from their NASA Key Strategic Mission Program Support Program. Mission Support Program. Okay, go ahead. What do you need?
That stick.
The stick. Oh, it's here. It just got small.
Hello? Can people hear me? Okay, so we were awarded the NASA Key Strategic Mission Support Program in December 2017, and then we observed in 2018. And so we were awarded 10 half nights for each year for 2 years. And our main aim out of that was to observe high-resolution follow-up imaging of about 60 events, including the planetary and stellar binary, to further develop the mass measurement method. So far, our priority has been to complete the planetary sample from Suzuki Plus 2016 mass ratio function, and also, if we have time, then do some mass measurements from planetary sample from MOA 2006 to 2014, so the 9-year analyses of it. And then if we have some time, which I don't know if we will have, then we can probably do some stellar binary mass measurements. So in this talk, actually, I would focus more on narrow camera observations. And for wide camera observations, you have to look for Josh's talk. So for first result, I would start talking about this particular event, OGLE 2012 Bulge 950. So this event was actually in 2012, but it was published in 2017. And this event, as you can notice, it had the microlensing signal was almost for 200 days. So as a result, you can, in 200 days, Earth is accelerating around Sun. So due to that, you can actually capture that acceleration in form of orbital microlensing parallax in the event. And you can actually see here you can see the difference in two different model where the red line shows the model without parallax and the data fits the model with parallax a lot better. So for getting mass measurements, we need actually 2 out of these 3 relations. So one, there's one relation, mass distance relation, that comes from the Einstein ring radius, that is from the finite source effect measurement. Then there's another one from the parallax measurement. And then there is mass luminosity relation, if we can detect the lens. So in this case, for this particular event, actually, we didn't have a good finite source effect measurement because so we just had a parallax measurement, but we didn't have a good finite source effect measurement. So in this case, we used this particular relation, and then also we tried to detect the lens and use the mass luminosity relation to get the mass measurement. So how exactly we get the mass measurement? So from light curve model, we can get the pi e, which we can insert into this mass distance relation. And if we can get lens detection, if we can detect the lens in high resolution follow-up, so from there we can get the flux, and we can insert that into the mass luminosity relation. And then we can solve those two iteratively together. And from that solving, we can get the lens mass and the lens distance. Since we already know the mass ratio from the light curve modeling, we can input that mass ratio in the lens mass to get the host star mass and planet mass. So from photometry, astrometry point of view, basically during the event, when we see the microlensing happening, the source is so much magnified that we should not be able to see the lens properly. And then as time grows, we should be able to see that the source and lens are separating out. And then after quite some time, we might be able to see that source and lens are totally separated out. So when we are taking the observation, it's almost in this situation. So we expect that the source and lens should be elongated. So here is the observation taken both with HST and keck at 5.83 years after the peak of the event on May 22 and May 23, 2018. And here, it was observed with HST I and V, and then also with keck K. And as you can see, that we clearly observe a lens and source elongation, and both in HST and in keck. And also, we measure 34 milliarcsecond separation between them. So we have done both single star fit, where in both HST and keck, where we see that there is some residual that doesn't look good. And then we did dual star PSF residual fit that shows it was a good fit. So this was the first time actually we were able to measure a separation of 34 milliarcsecond with keck narrowband. So with the measurement, when we actually detect the lens, with that, we can actually see the separation of the lens and source. And since it was taken 5.83 years later, we can actually measure the mu rel, the relative lens source proper motion. And you can use that mu rel to constrain the pi e. So here, this is the pi e that we have from light curve. And you can see that in east-west direction, it is kind of well constrained. But in north-south direction, it has all these uncertainty. And also the best fit model actually shows kind of this region. Whereas when you put mu rel constraint, you can see the best fit model goes here, and also the uncertainty is very low. So from that, we can actually really constrain the mass measurement. So it is reflected over here also. You can see that this pink shaded region, the pi e, actually shows this big uncertainty that comes from the light curve modeling, whereas with mu rel determination, this green shaded region actually shows that how much the uncertainty is reduced because of the measurement of mu rel. And then the orange and gray and blue, these three are the mass luminosity relation. These three are coming from the flux that is measured in K band, I band, and V band. And inputting those in the mass luminosity relation, we can get the mass distance. And this is the solution. So also, you might have noticed that this event was, as I mentioned, it was on May 22 and May 23. And so this was not actually a coincidence. We actually we actually asked for a HST proposal for a near simultaneous Keck and HST observation. And our main aim with that was to do color-dependent centroid shift to find the lens to measure the lens source separation. So how that works is basically if the lens and source if they have different colors, especially if the lens is redder than the source, then we can see that in K band, in infrared, the lens will be kind of brighter, whereas in V band, which is a blue pass band, we can see that the lens will be way fainter. So as a result, because of this kind of flux difference, we should be, here you can kind of see the illustration where the source is actually way brighter than the lens, and the centroid is closer to the source. Whereas in I band, they kind of have equal. So the centroid is kind of moved in the middle, and then the centroid kind of moves further towards the lens. So in this case, actually, between V and K, the centroid shift was of the order of a few milliarcsecond. So we wanted to measure, so if you can measure this shift in centroid, then you can measure the separation between the lens and source. And this method can be very useful, especially if the separation is smaller at 10 to 30 milliarcsecond. But in this particular case, this was a pilot program, so we tried to do as best as we can. But we still, I would say this is more like a preliminary method, and there were certain challenges. We didn't do the astrometric precision. We didn't reach as much as we thought we can, or as much as we should, probably. So the challenges with that is like, okay, we need the source and lens to be of different colors, which in this case it is. But for increasing the astrometric precision, we think we need way more deterred images, especially, so these particular observations were done with HST-I 6 deterred images, HST-V 8 deterred images, and for Keck, this kind of observation for narrow passband, narrow camera, you need at least 30 to 40 images with less than 100 mass FWHM. So that is something like, it really needs a lot of deterred images, basically, to get this kind of astrometric precision. And we think that maybe instead of 6 deterred images of HST or 8, if we can get like 10 or 15, that can definitely increase the astrometric precision. Also, another problem was there were not enough stars sometimes, and that is probably a problem of this particular field, that there were stars that were there in K band, but in V band, those stars were too faint. So that was another problem, that maybe with more images, and maybe some other fields may not have this kind of problem. It's probably in the field there were not enough stars. So finally, I would like to just show some of the observing challenges with KEC-AO. So it takes about 60 minutes of observation time to do this kind of really high resolution and high precision astrometry on each target with small deter pattern within the 2 to 3 days interval to do this kind of KEC observation. So that is very high in time cost. And also, obviously, there's like always, like there's weather problem, there's like earthquake, the AO correction is mediocre, the laser closing time, so et cetera, all these problems always come up. So as a result, the effective observation time is at maximum 3 hours per night if the weather is good. And on average, we can do about 1 to 2 such high precision target per night. So it is a very time costly thing to do. Also, because our targets are very faint, we actually need about, in 90 to 95% cases, we need laser guide star. We tried with natural guide star AO correction, and at the distance of our target, it is not very suitable for this kind of high precision lens source separation measurement. Also, so in this kind of case, if the weather is not that good, we can just, at that time, we can take wide images, and we can just get the total flux measurement. We don't have to confirm the lens with the lens source proper motion. So Josh is going to talk more about this kind of flux measurements with wide camera. And finally, the science goals of this program. So we want to obtain the mass function instead of the mass ratio function that is in the Suzuki sample. And for that, there are like several steps that also we need to still develop to get to the mass function. First is like we need to still develop the mass measurement method. Second is that the detection efficiency that's related with this lens detection in high resolution. So even though like we can detect the lens, like if the source and lens brightness is very different, the ratio of the brightness is very different, or the separation is very small, then we have to understand that our detection of lens will depend on this kind of parameters. So we still haven't really developed how we are going to take care of that detection efficiency part with lens detection. And also, we have to incorporate this kind of thing into the completeness for mass function statistics. So this is something because we might do this, we will do this kind of similar type observation with W first, so I guess we have to still think about this kind of problem for W first as well. Another science goal is to compare the mass function to planet formation theory predictions. And as you know, this the observed mass ratio statistics from Suzuki sample is being compared with the core accretion theory, 2 different models of core accretion theory. And this particular event actually just 39 Earth mass, it is found, the planet. So that is right kind of on the middle between this mass, in this mass ratio region, where it is like at the peak, almost close to the peak. So it's between this 20 to 80 Earth mass planets. So we really want to see that is this gap here between 20 to 80 Earth mass that we see, is that gap really, is it an artifact of the mass ratio parameter, or is it like, is it really there? So that is another thing we want to check. And finally, another thing that we want to do is something that Yutong already showed yesterday, is like basically how often do we see this kind of excess flux? And we can check with the excess flux. We can take the excess flux and do the probability, and from there we can check the galactic model. The assumptions that we are doing on galactic model, are those correct or not? So yeah, that's all I have. So.
Okay, questions for Arpana? Andy.
So, could you go back to the parallax diagram for 950? So, when Ghosh et al. Introduced this method, they noted that there would be a degeneracy in this from U naught plus and U naught minus for such, going from one-dimensional parallaxes plus proper motions. But you just seem to be showing one of the two U naught diagrams, maybe the U naught minus one. Is that correct?
Yeah, this is what I got. I don't know. Dave, would you like to answer?
It's both? Oh, I see. They're overlapping. Uh-huh. Okay. So then, so they're overlapping, but then they're actually overlapping very tightly in the north? This is heliocentric diagram?
No.
No.
Okay.
Yossi.
How well do you think this method will work on bulge lenses?
For W first.
W first.
So yeah, if it is like about 3 milliarcsecond per year and 4 years difference, so like about 10 milliarcsecond, 10 to 12 milliarcsecond separation. So I think it's doable. Still, maybe it's still doable if the brightness are kind of similar, then we can try to do it. I think it's doable, but we cannot do it for all the cases. And maybe we will use TMT for that. So if TMT gets built, I mean something like some ELT system.
Valerio.
Assuming a source distance at the right clamp, or you have an independent measure of the source distance in this case?
No, we are using like a galactic model and getting the source distance. That's
Okay.
right.
So how sensitive is the final result to this assumption?
Yeah, so if the source distance varies like about 0.3 kiloparsec, the result doesn't change. Because like, there's like there's a distribution of the source distance, and from that, it's...
Dave.
The final mass is constrained both by the flux measurement and then the parallax and the measured relative proper motion. But the constraint on the mass from the parallax and the measured relative proper motion depends only very weakly on the source distance. It's only the conversion from between geocentric and heliocentric proper motions that depends on the source distance for the parallax.
Okay, I had a question, Arpan, about for using this method for W first. How does it influence our selection of filters? Because W first right now isn't going to have a K. Does that limit the ability to use this method?
So W first is still going to have an infrared, like which is kind of between H and K.
Yeah.
And then, so that's another thing about the the centroid shift method, color-dependent centroid shift method, because if we think we can do really good, so probably it's worth of going for a blue band. But if we think that, oh, we cannot do that good, then it's like, we have to think about time cost. And also like a lot of another thing is a lot of the, as I said, that in a lot of the stars will come up in K band, but they were not coming up in V band. So you also have to think that how many of them we can actually get out of, like how much we are going to gain having like a bluer band.
Bluer band as opposed to red. Yeah.
Right.
Okay. Okay. Anyone else? Okay, let's thank Aparna again. All right. Unfortunately, Kalen's sick, so he's not here. So we're going to ramp up the schedule, and Josh Blackman's going to talk now about adaptive optics follow-up of a super Earth and a giant planet. I'll let you read the source names, Josh.
Okay, so firstly, thanks to Aparna for basically giving an introduction about what I'm about to talk about, so I don't have to talk about that part. I'm a grad student from University of Tasmania. I'm a final year grad student, and I work with JP Bellier, Andrew Cole, and Katie Vanderoo, who is a first year PhD student. So I'm just going to talk about a couple of objects that we have observed, followed up with Keck in order to constrain the lens flux. So firstly, as I'm sure everyone knows, normally when you model a microlensing event, you don't get the physical parameters straight away. You have to use a galactic model. When you do that and you determine the physical parameters, you usually get it to 30–40%. So aside from the mass distribution function that Aparna was talking about, one reason why you might want to do follow-up observations is to constrain the lens flux so that you can constrain the mass distance of the lens. So this particular event was in JP's paper from 2018, and you can see the different constraints, one for the theta E constraint, one for parallax and Spitzer. And then if you take out this blue line, you have a fairly large error bar. And so from Andre's original paper, he gave two results for the planet mass of a half Jupiter, one U bigger than naught, one U less than naught, and then when you add in the Keck observation, you cut the error down by from 30–40% to less than 10. And in this case, not only do you do that, but you're able to break the degeneracy by this Keck and isochrone line, which then places your constraint on the lens mass and distance in a different place in this case. So that's one reason why you might want to do this. So I'm talking about three different events that I've worked on. One is this one, which I talked about last year. I'm not going to spend long on this. This was as Martin knows, a binary event from the late 90s. And we attained Keck data on this in 2013. Virginie Batista, I think, observed this. Unfortunately, despite the 16.07 years between then and the observation and the lens proper motion of 3.5 milliseconds per year, we weren't able to resolve the lens and the source, partly because the lens was also really faint. So there's a very large flux differential between the lens and the source. However, what I did do is remodel the event using limb darkening parameters and also modeling the blend of each telescope, which was not done back in the old days of microlensing. So here in maroon are the points from Mount Stromlo telescope, which weren't used in the original study. And I did a variety of models, one without the Stromlo data and one with the Stromlo data, and then rescaled the parameters as is fairly standard these days. And so you can see the value for S and Q are fairly similar to one another in the new model, but they're all sort of offset from the old one. And the chi-squared degree of freedom is slightly better. So this is the Keck image from this particular event. And because we couldn't constrain the lens flux, we just did a standard Bayesian analysis with the galactic model courtesy of Naoki Koshimoto. And we confirmed the original study, which was that it was a M-dwarf binary, maybe a brown dwarf binary. So we could observe this again, but it's a binary event, and people want to look at planets, so this is not the most exciting one. This is slightly more interesting. So this is follow-up on
2017-1434, which was published by Andre in 2018. This is a super Earth planet. What's notable about this is that it's really, really close. So it's 0.86 kiloparsecs, which provides some challenges when you're trying to come up with your mass distance diagram, because your isochrone constraint doesn't has to work very hard to try and break the degeneracy. So you can see the caustic, the large dip on the caustic crossing as it crosses the resonant caustic here. And so this one we observed as part of the program Apana talked about last year in August in K-band on the wide camera. This was towards the end of the run when the weather was getting fairly sketchy, but we still managed to get some decent images. So this is the image from the wide camera, and we have the cut-in of the source located over there. All of the Keck data that we've been working on in Tasmania has been reduced with a pipeline that myself and Katie wrote in Python, just to do all the standard flat filling and that kind of thing. Astrometry at the moment is still done manually, although I think there's some code lying around to do that automatically, and we may be joining those two things together and putting this on GitHub at some point if anyone is interested in that. So for this particular event, we have a magnitude of this thing over there is 16.61 in KS. And from Andre's paper, we convert the V and I and to the predicted of 17.59, make the reddening connection, which is, correction, which is tricky, trying to sort of reverse engineer what Andre did in his original paper so that we use the same correction. Where we use the standard intrinsic magnitude of the red clump offset from Nataf 2013 in doing this. And then we get our blend magnitude of 17.03 plus or minus 0.11. And so now we have that, we can plot our mass distance diagram for this particular object. We get something like this, which is not, because this lens is really close, you can see here, this is the isochrone line. It's basically lining up exactly with the theta E constraint. So you're not breaking any degeneracies here, but you can see Andre's point there is basically bang on all three of these constraints. So again, this is a confirmation that Andre's model is not insane. And so if you put my point on, it's pretty much going to be at the same point. This is, of course, assuming that 100% of the blend is from the lens. And given the proximity of how this works out, we think that's a fair assumption. When I'm writing this up, I may do a contaminant analysis, as Apana mentioned, as Naoki and also Virginie have done before. However, I don't think that's really going to show anything because it's kind of all in this plot here. So they're the end-up numbers. The numbers are essentially the same, but the error bars have been chopped in half, a little more in some cases.
Wait, did you put in just theta E and photometric, or you put in the original parallax measurement as well?
The original parallax is in the
It's
red
in the
constraint.
original, but is it in your point, or you're just doing your theta E plus your emission measurement?
You mean to determine this point here? I mean,
Blackman point,
yeah, I mean, it's weighted from these three constraints. So it is including the parallax in that sense, if that's what you mean. Yeah. So finally, I'm just going to mention 477. This is an object that is potentially very interesting. I would put this under the future work category. I've just started on this. This was published by Etienne in 2012, which is a 1.5 mass Jupiter. And this object is interesting because it's got a really, really large proper motion. So that means even though it's only 7 or 8 years ago, we might be able to resolve the source in the lens, which is why we've observed this frequently on Keck over the past 3 or 4 years. And so this is when they were observed in both wide and narrow when the weather permits in H and KS. this is the original Ogle-3 image, and at the point of the source is the red point here, and the arrows pointing to the blend. This is from Etienne's paper. And so, of course, we can plot our cake image over the top of that, which is much better. And then blow that up a bit, and then blow it up again. And so this circle is showing the what was in the object on the original Ogle frame. And so the question is whether or not this thing is the lens or not. So this is the source, and this is something else. And so we're hoping that this thing was going to move between 2015, 2016, and 2018, but it didn't. So this is at 110 milliarc seconds apart, and it just stayed there. So more than likely, this thing is an unrelated companion to the source. And then it's a matter of measuring the flux of the source, which is what I'm working on literally like last night, which I haven't done yet, is determining the flux of this thing. And so there's a few options of what this might be. So the first thing we're going to try and do is do what Apana did for 950, which is measure the PSF elongation in this and hope that we'd be able to measure the centroid shift. On a first glance, it appears that that's probably not the case. So the other question would be whether or not there's any excess flux in this thing. And if there's not, potentially that could mean maybe it's a white dwarf and a Neptune, which would be pretty interesting. But all that's very much stuff that I will be working on shortly. And with that, I think I will end 1 minute early and take questions.
Any questions for Josh?
So is there no motion at all? So could it be something bound to the source?
This one?
Yeah.
So you get, no, there's no motion at all.
So
As far as I can tell, it's
relative to the source or relative to
relative to
everything
the
else?
source.
Okay.
Yeah.
What was the proper motion in the original paper?
It was 10.2 or 3 milliseconds per year in geocentric. In heliocentric, it's like 13 to 14, I think. And this was, 8 years ago, I guess. 7 since the observation.
Okay, anybody else? Oh, Jennifer, do you have a question? Or?
Sorry, no, I'm doing 15 times 8 in my head and I'm a little tired.
I guess the question is, Josh, should you see the should you see the
I thought you were going to say, what is
lens?
the question? Fuck, what's 15 times 8?
No, go ahead, Jennifer.
Yeah, you go.
120.
Yeah.
Yeah?
120.
So like a tenth of this image then? No. Yes? No. Yeah, a tenth of this
yeah.
image. So, I mean, it's at the right separation
Yeah,
to be the lens, but it's not.
but it hasn't moved at all.
Well, but, okay, so how much would it move?
So 3 years ago,
It would
which
be
is I guess half,
45.
I don't know, 2/3 of the time.
Yeah.
It should have moved, what, 80 to 110 or something like that.
But then doesn't that also imply that the lens is not luminous in this? Like, because you said you were looking for elongation, but it seems like it should just be separated, unless it's super faint.
Yeah,
So
I mean,
maybe it's an upper limit. Is that okay? Yeah, but I mean that's what you say. So yeah. Okay, cool.
yeah,
Thanks.
it's on the it's on the very edge of what is feasible. I think. Like, I asked that exact same question of like, surely if it's moved, it's either on really the edge of this PSF or it's like that's the closest it could be. But
Arpana.
So just a comment on that. Actually, this is 2010 event, but like we had data, I think 2015 or 2016. So
Yeah.
when we calculated like the 13 milliarc second in heliocentric, so in 2015 you will be expecting 65 milliarc second separation, and we were getting 110. And then like we were like, oh, maybe there's something wrong with the relative proper motion prediction from the light curve. So let's take data again and again, and then we saw, oh, it's just sitting at 110. That's what basically happened.
We got folks puzzled. That's good.
I mean,
Anything else for Josh?
I agree. But yeah.
All right, let's thank Josh again, please. Okay, and after a technology interlude, Fumio Abe is going to talk about massive black hole search by MOA.
Thank you. Okay. Can you hear me? Yes. Okay. So I'd like to report the progress on the massive black hole search by MOA. This is done by one of our master course student, Hisashi Munakata. Okay. As many people mentioned, the detection of gravitational wave by LIGO make it clear that the population of about 10 solar mass black holes are very common. But unfortunately, no electromagnetic counterparts are detected. So we can't know where they are and how many. So as you know, microlensing is a unique method to detect massive compact object regardless of its electromagnetic emission. But to detect high mass black hole need long-term observations because the time scale is very long. And another very serious problem is so-called microlensing degeneracy. As you know, transverse velocity, the mass of the lens and distance to the lens are degenerated in single observable parameter, TE. So it is hard to distinguish low proper motion stars and massive black holes. To break this degeneracy, we need to observe parallax and theta E. Parallax is pi E is inverse of projected Einstein radius, and ordinarily we can obtain theta E from the finite source effect, but in case of black hole lensing, detecting finite source effect is very difficult. So we must use astrometric microlensing. Okay. Anyway, first stage for the black hole search, finding long time scale events is very critical. As you know, we have long time scale data, both for galactic bulge and Magellanic clouds. He used long-term galactic bulge microlensing data between 2006 and 2014. after reducing the data, he selected microlensing events using some bump filters. Then he obtained 2,243 events, 43 candidates. Then he made single lens fits to those events and selected long time scale and small chi-square divided by degrees of freedom. Then most of the binary events are removed. Then 137 events remained. Looking at those events, he found some events problem caused by the high blending. So the parameter U minimum and T are degenerated. As you can see, this event apparent has a short apparent time scale, about 20 days, but obtained time scale TE is 190 days. So that means TE values are poorly determined. So he removed such kind of events. Then 88 events remained. Then he made parallax fits to those events. This is the pi distribution, pi e, and number of events. This distribution peaked around pi e around 0.25. But the problem is typical value for pi e for black holes. So we have calculated pi e values for several mass. This is pi e versus distance to the lens for 30 solar mass, 10 solar mass, 3 solar mass, and 1 solar mass. As you can see, black holes pi e is small. So he selected events pi e value less than 0.05, and only 5 candidates remained. Looking at those events, this is one of the candidates. As you can see, this is relatively clean single lens events, and no parallax can be seen. Actually, all those all 5 events has the pi e values for those events are consistent to 0. So we couldn't constrain pi e. So it's hard to distinguish if those events are real massive black holes or ordinary stars in the galactic bulge. However, if the astrometric microlensing, if we can obtain theta e from astrometric microlensing, we can constrain mass of the lens. This is the theta e versus pi e for various mass. If the mass of the lens is small, theta e is very small, but if the lens mass is very high, somehow astrometric shift would be detected. So to find black holes, measurement of pi theta e as well as precise determination of pi e would be critical. So 88 events were selected from bulge data between 2006 and 2014. From parallax fit, 5 events were selected. However, pi e values were consistent to 0 for those events. So precise measurement of pi e and astrometric observation would be important to find massive black holes. So thank you very much.
Questions? Yeah, Andy.
So all the events had internal MOA identifiers. Were they also MOA alerts?
Only more data.
Right, but were these MOA alerts? Are they designated MOA events?
Sorry, I didn't check.
And so did you check to see if there were OGLE data for these to improve the parallax measurements?
Yeah, I think so. Yeah.
Yeah, Valerio.
Maybe your cut is too severe. 0.05 maybe is too much. But if you release it a bit and include some more events, do you get what's the first event for which you get a non-zero measurement for the parallax?
Yeah, maybe too severe.
Yeah. So maybe if you do you know whether in your sample there is one event which has the lowest parallax that has been robustly measured? Maybe you can study that event and then say something at least on it.
Yeah. Somehow.
Yeah.
Okay. Yeah, Roddick.
Showed the table. If you could go back to the table with the 5 events, the 2 are not that way. Yes. So you have shown one of the light curves, but just looking at the results for the 4th and 5th event, timescale 178 plus minus 178. It seems this event is really not good quality. The 2 on the right. And
Right.
parallax uncertainty of 2.02 also seems questionable how this light curve really looks like and what's the quality of the data.
You mean this one? Time scale? Yeah.
Both time scale and parallax uncertainty seem very large.
So it should be removed.
Uncertainty
Sorry.
being very large. That's not. Sometimes you don't measure parallax, or sometimes you place only very large constraints. And sometimes
This
even
is
constraints
also
are interesting. So
very
like
poorly
0.004 plus or minus
determined.
0.2 is an interesting constraint on a parallax. And even there are cases when plus or minus 2 is an interesting constraint.
Yeah. Yeah.
Okay, and anyone else? All right, let's thank Fumio again. So next, we have Hiroko Nakura talking about new constraints on PBH abundance from microlensing observations of M31 with HSC.
Good afternoon. So I'm Hiroko Nikura from University of Tokyo. So today I would like to talk about the search of microlensing effect by primordial black holes targeting at the central region of M31. So the target of our study is the dark matter candidate around our galaxy. So among several dark matter candidates are proposed, we focus on a feasible candidate called primordial black holes. So primordial black hole is proposed to be generated in the early universe and can survive as dark matter candidate if they are not evaporated until today. So in this study, we searched magnification event due to microlensing effect by primordial black holes. So this figure shows the parameter space of primordial black holes studied by previous works. So x-axis shows the mass of primordial black holes, and the y-axis shows the fraction of primordial black holes to the total dark matter. And this shifted region shows the constraints by previous works, and these four regions correspond to the previous microlensing constraints. Then, as you can see, there's an open window for abundant primordial black holes with mass around from 10 to minus 15 to 10 to minus 9 solar mass. And in this study, we targeted this mass range primordial black holes. And since for this, since we can expect around time scale with around 20 minutes events for this primordial black hole microlensing, so we performed dense cadence observation using many background stars at the M31. So next I will talk about our study in more detail. So this is a Subaru telescope, and this is hyperspin cam. It's in the prime focus of Subaru telescope. And so hyperspin cam is composed by 104 CCDs, and so the field of view corresponds to 1.8 square degrees. And this picture shows an example picture targeting at M31 central region taken by HSC. So as you can see, HSC can nicely cover the central bulge and disk region of M31 with single field of view. And also, HSC can go deep into around 24 magnitude with around 90-second exposure. So next I will talk about the estimated event rate for around assuming one night observation. So this figure shows the event rate of microlensing effect caused by various mass primordial black holes. For example, here we assume that all dark matter in the Milky Way and M31 is composed by primordial black holes. And if we assume primordial black holes with mass, for example, 10 to minus 8 solar mass, the time scale of microlensing event will be around 30 minutes. And if we assume observation up to 7 hours, so we can cover, we can expect high event rate from primordial black holes from around 10 to minus 11 to 10 to minus 7 solar mass. So next I will talk about the detail of the observation. So as I mentioned, we searched microlensing effect events by primordial black holes using HSC data. So we monitored this central region of M31 for around 7 hours, and we take images of this image every 2 minutes. So in total, we take around 200 images of this field and searched microlensing event in this field. So far we performed this observation twice, once in 2014 and once in 2017. So for the detection of search of microlensing impact from these 200 images, so we performed image difference technique to search the transient candidates among this dataset. So for difference imaging technique, we compared two images with different epoch and make subtraction to create one difference image. So if variable stars included in this field like this, the difference of flux shows up in the difference image like this. So let me move on to the results section. So this figure shows the distribution of transient candidates from 2014 observation. So we succeeded to detect around 15,000 transient candidates from single night observation. And the number of transient candidates for 2017 observation was around half compared to 2014 observation because of the poor seeing condition compared to 2014 observation. And among them we can find some, we can write very beautiful light curves like these flare events or eclipse binary candidates. So next we use these transient candidates to search microlensing event. So first we have around 15,000 candidates for 2014 observation, and we perform event selection for this dataset. So we basically for section conditions performed for Kepler's microlensing search. So we did event noise selection, noise cut, or do microlensing fitting for all light curves. And by this section, we still have 66 candidates. And for this, we performed visual inspection. And for those remaining candidates, and most of them were actually junk events. And for example, and most of the junk events were coming from the spikes around bright stars. That is showing around this. So these kind of bright spike events cause this kind of fake light curves. So then we need to remove them by eye selection. And however, we still have one remaining candidate from our dataset. So this candidate is around 24.5 magnitude, and so it's very faint candidate, but it's nicely described by microlensing light curve. And it is difficult to tell if it's real event or not, so next we look into the property of this candidate using archival data taken by HSC. So this lower panel shows the light curves of this remaining candidate using our observation in 2015 and 2017. And this blue line shows the 1 sigma level noise of these images. And as you can see, for 2015 observation, we cannot detect a significant time variability. And for 2017 observation, we can see very strong correlation with the variation, time variation seen, but we cannot detect significant time variability that passes 5 sigma level. So we conclude that this candidate is unlikely to be periodic variable stars, so we remain this candidate as feasible microlensing candidate. So far we have one remaining candidate, but we may miss some candidates due to noise or selection criteria. So for discussion, we estimated the expected number of microlensing events from using our dataset. So the expected number of microlensing events can be expressed by this equation. So we evaluated these 3 factors using observational data. The first factor is the number of stars in the field, so we counted the number of significant peaks in this field. For event rate, we calculated assuming one night observation, and so this means that the event is high event rate because higher for the primordial black holes from 10 to minus 11 to 10 to minus 7. For detection efficiency, we performed simulation of light curves and bright selection criteria by we applied for event selection. So this figure shows the detection efficiency from 2014 observation, and the detection efficiency will be around 60% for bright stars, and for faint stars around 25 magnitude, the detection efficiency will be around 30%. And the detection efficiency gets around half for 2017 observation, and yes. And so far we evaluated this event rate by assuming point mass approximation, but we still need to consider another 2 effects, even especially for light mass primordial black holes. For example, so the first effect is known as wave effect, which happens when the Chivalry shift radius of primordial black holes is smaller than the radius of the wavelength of the observation. So, for example, if we assume around 10 to minus 11 solar mass primordial black holes, this W factor is around 0.02. In this case, as you can see, the magnification is totally suppressed compared to geoptics case. So, as you can see, this guy, so the primordial black holes with greater than around this mass can be totally suppressed by this wave effect. And also, finite source size effect also suppress this magnification for the lighter mass primordial black holes, so we need to take into account these two effects. So how we evaluated this factor, and we only have one remaining candidate, so we put constraint on the abundance of primordial black holes to the total dark matter. So this shaded line comes from the 2-day observation, and even from 2-day observation, we can put the tightest upper limit on the abundance of primordial black holes to this around 10 to minus 11 to 10 to minus 6 solar mass. Yes, this is a summary. So we succeeded to put the tightest upper limit on the abundance of primordial black holes for this mass range. So as a future prospect, we are planning to do year scale observation, and we are trying to constrain around this mass range primordial black holes from HSU observation of M31. Unfortunately, we can't constrain light mass primordial black holes due to wave effect, but in the future, experiment with X-ray satellite observation pulsars can constrain, expected to constrain this mass range. Thank you very much.
Valerio.
Actually, in the literature, there is another constraint there between Kepler and femto. It is the neutron star capture, but you didn't mention it because it covers all the gap in between Kepler and femto.
Yeah, but it other constraint by neutron capture or other things contain some uncertainties for the scenario, so we remove this constraint from the constraint figure.
Matthew, right? You're behind the pole, so I can't.
So 2 questions. One, how did you estimate the number of sources that you're effectively monitoring? And 2, have you tried converting these constraints into constraints on free-floating planets just by using a different density and velocity distribution?
So for the first question, so we estimated the number of source stars by counting the significant number of peaks in the figure. And for second question, so since our constraint is more lighter than planet mass, so we haven't considered.
Okay, let's thank Hiroko again, please. And last up for the session, Nathan's back again to talk about strong and weak microlensing in the 2020s.
Nathan, until we get the center projection working, if you could present from the sides, that'd be greatly appreciated.
Okay.
Thank you.
So I'll go over here for all the people who've had to wait for people to point out that one yesterday. So I'm masquerading as Will, who, if you were here yesterday, you might have seen him for a minute. He's had to take off for the week, so I'll present his talk. So strong and weak microlensing. So just want to lay out what that means. So we all know microlensing is strong lensing, but unresolved. So strong microlensing is really just strong lensing within the Milky Way. So it's been observed once, and I'll talk about that a bit. It's really challenging just because of the resolution. You can't always resolve that, and we might be able to do it in the 2020s, and that's what this talks about. Weak microlensing is a little bit different, and this came up when we were talking about the 100,000 solar mass black hole in a globular cluster. There was Jessica asked a question about many stars nearby and if we could correlate the lensing signal from them. That's basically trying to do that. So that's weak microlensing, and I can take credit for coining this term because I was a weak lenser in grad school, and weak lensing for galaxies is basically correlating the really small lensing signal you would expect. Sorry, I'm over here because the center projector is broken. So what you're trying to do here is look at multiple sources that are order 1 or just a few Einstein radii away and correlating the signal. And the caveat here will be that is extremely challenging to do. So for strong microlensing, which again is resolved microlensing, the big thing here is that the Einstein radius is just small. And so you can't resolve it very easily. So here's just a map of what you expect for the Einstein radius for different masses and distances to the source, or to the lens. So if we can do this, it's really great because we can get a single epoch approximation of theta e, because you can actually see the separation between the two sources of the stars. One problem, though, is that usually you're going to need, I can come back over here. Usually you need a pretty massive lens for this to be the case, and therefore the time scale for this event to occur is really long. So there's some ups and downs here. So we should point out that this happened once in optical astronomy, or maybe infrared, and also, but it's happened also in radio interferometry. So this is VLT interferometer and VLB, which I don't really know what that stands for, but this was in radio sources. But this is going to be tough because you need radio loud stars, which would present their own problems. And this is a recent paper, which I noticed Andy's on. This seemed to be a really lucky nearby low mass lens. So most of the rest of this talk will not be talking about this lucky alignment of a small lens. We're thinking about more massive things. So we really think that this can be something that can be done in the 2020s. So here's the resolution of different telescopes. And so for LIGO mass objects in the 2020s with the 30-meter class telescopes, we should be able to start to resolve the multiple images of source stars at the bulge. Now, if you believe that there's 1,000 solar mass black holes floating around, maybe we can do it now. So what will this look like? So there was I'll go back. There was a quote at the end of the abstract of this paper saying that this might bring up the fact that you could observe the Einstein ring for a source star. That might be tough because the resolution here is much larger than the image size. So you're probably just going to see 2-point sources. But if the images get close, if we can get the resolution down to the source size, maybe we can start to see some elongation of the lens images. And then, so here's the source image size. And so only for ELT will we be able to see that elongation. So this is I want to start it over. So this is I'm going to preface it. So this is the TMT adaptive optics PSF and then a lens. So I'll play it a few times. I guess it'll probably just go back and forth. But you'll see the source start to appear, and there it is. So these are the parameters that were injected here. So I think Will injected this in with GalSim, which is a pretty good tool for doing something like this. You can watch it a few times. So remember, we're looking at a massive lens. This is years here. So you'd really have to do AO observations many times over to really see this. And you can imagine doing this once and seeing, if you pause it in the middle when there's 2 objects here, you would just see 2 objects, and it's hard to say these are 2 images of the same star and not just 2, like a nearby binary or something. So there's going to be some challenges here that we need to map this out, but it is doable. Here's some additional challenges that Will and I talked about yesterday. So you'll have blending. So if you have multiple images and there's background stars within your PSF of your adaptive optics system, they'll be blended together. That'll be tough. You'll need to have bright sources, and for the very massive lenses, you'll have to observe it for a very long time. Okay, so now on to weak microlensing. this is not going to be easy. So it was brought up once today. I'll go over why it won't be easy. So what we're trying to do here is you have some lens with an Einstein radius, and there's a source being lensed. And then maybe there's other nearby sources that are weakly being lensed, and you'll want to correlate this. So it would be very powerful to be able to do this. If you could see how the lensing is happening on nearby stars, you could get an actual proper motion directly from this. And everything would be great. But to do this, let's say you can measure 1% effect. So the magnification falls off as the Einstein radius to the -1, but then outside of the Einstein radius, it goes to the -4. So you can really only go out to a couple Einstein radii to see anything if you can measure at the 1% level. Now, luckily, the astrometric signal kind of stays to the -1, and so it might be better to use the astrometric signal to make this measurement. So usually, I apologize, these are Will's slides, so I'm trying to decipher it as I go. Yeah, so the blending. So when you have these multiple images for different stars, there's a lot of things going on. And so to fit all this underneath these AO systems, or these AO systems would be required to try to pull this apart. The last thing is just how likely is it for two stars to be near each other or near enough such that a couple Einstein radii overlap more than one star. So here's a LSST projection Radek was involved with. And then this is from Casey Lamb's popsicle, which she talked about earlier today. And then Matthew Penny told Will that you could get up to 10 stars per arcsecond squared. So we're kind of working in the 1 to 20 stars per arcsecond squared. And so you're going to need a pretty big Einstein radius to intersect that. So if you look at the 2-point correlation for this, it kind of goes linearly with the separation you want to do. So if you want the probability to be high, you need a large Einstein radius. And so this is showing that for LIGO mass events, only 1 in 1,000 LIGO mass events will have a second star nearby that we could try to make this measurement with. And if you do believe that there's 1,000 solar mass black holes in the Milky Way, then maybe 1 in 10 of those microlensing events would have a second star nearby that you could try to correlate the signal with. So in summary, strong microlensing is probably doable in the 2020s, and weak microlensing, probably not, unless we're really careful or lucky. So I'll end it there.
Okay, questions for Nathan?
If you use the term strong microlensing, how do you define microlensing?
Yeah, microlensing is unresolved strong lensing. And then, so microlensing is in the strong regime. So I'm gonna, by trade, I'm an extragalactic astronomer. So strong lensing for me was, multiple images of galaxies. And strong lensing there is in this nonlinear regime, which is exactly the regime microlensing is in, but it's unresolved. So that's kind of why it got a different term. But in full technicality, microlensing is strong lensing.
Well, if we're being careful, we should call it strong millilensing.
Right. Hey, Will and I were just talking in our offices, and we just these are the terms we coined, and maybe if this happens in the next decade, we can call it Golovich lensing or something. I don't know.
Jessica, you had a question, right?
Yeah, can you go back to your rate estimates or the number count maps?
Yes, this one.
One more back.
Sure.
Sorry, the one with the map on it from Casey's thing.
Oh.
Yeah,
here.
This is for LSST, but you're saying even for W first, it's not enough stars per square arcsecond?
So this is from LSST, which maybe Radek could tell us more about, but this is a plot from their paper, this paper. And I'm not sure if this is what Will did, but I think he just looked here and got the densest part.
Okay, so W first doesn't actually help all that much relatively speaking.
So Matthew, I didn't have this conversation you did with Will. Where did this number come from?
What magnitude that was, I have no idea.
Okay.
If you go all the way to the bottom, it comes out to about 70, but that's really faint stuff.
Okay.
Okay, Andy, you had a question.
Yes.
I couldn't quite understand what was the point of the weak lensing, but it's not satisfactory to have binary sources.
The motivation is just this came out from, I think, okay, so Will and I were talking in his office, and we thought, what if like a globular cluster with an intermediate mass black hole got stripped and pulled into the galaxy? What if there's this 100,000 solar mass black hole floating through? How many stars would it lens? That was where it came from. And so we just kind of drew this up, and then we thought, well, what could you gain by looking for something like this? And it's really just the proper motion and a more direct measurement of theta e.
Yeah, go ahead.
I thought anyway, my question remains the same. So what's wrong with binary sources to produce this?
Binary sources to produce this. Well, I guess so if the second source is outside of the Einstein radius. I mean, we're just really doing a thought experiment here. I'm not sure how to answer your question.
But anyway, you're giving numbers like 10 to the minus 8th or something. But anyway, there's like 10 to the minus 2 chance that this will happen. The binary sources.
Where are you getting this number? I'm not following.
Well, because 100% of stars have binary companions, and then they're distributed in log normal way. So anyway, there's 10% of them, 20% in a couple Einstein radii.
Okay, I'll take your word for it and think about it some more.
So is it actually more feasible to do around supermassive black holes around the center of the Milky Way? There, the black hole is much more massive.
Yeah, I guess if you can find background sources behind that.
Sure.
It'd be tough, I guess, just all the dust and stuff. But
okay, David.
It would be more feasible if you could see them. Yeah.
So prior to going for the coffee break, you said that there's a low probability of seeing this. Are you willing to go on the record and say that there's no great hope of ever observing this phenomenon?
Let me remind you that this is. I'm going back away. Sorry, this is a little slow.
You can speak for Will. Right?
This is Will's talk, so
Yeah.
Will might have go on the record. I'm not going to go on the record. It's possible, but I think it's going to be tough. I was intrigued when Jessica asked the question about the globular cluster lensing, and we were looking at the multiple bulge stars that were behind it in Kaiosh's talk, and it was interesting. I think it's doable, but I had this slide up, and it's 1 in 1,000 for LIGO mass events. It's low chance. I mean, we don't have very many LIGO mass microlensing events at all. We need to find 1,000 before we expect one.
Okay, anybody else? All right, let's thank all the speakers again, please.